Hi, this is John Whitaker for the Mathematical Analysis 1 class, and this is our 28th video lecture. And we're talking about continuity, and now we want to talk about continuity along with vector value functions. And so the first thing I want to do is write up the theorem. So this theorem states, well, it has two parts. And it says if you let f sub 1 all the way up to f sub k be real functions on a metric space X, and let f bar be a mapping of x into Rk defined by f bar of x is equal to f sub 1 acting on x, comma, f sub 2 acting on x, all the way up to f sub k acting on x. And that's for all x, not only the big x, the little x's are the input values. Then, f bar is continuous if and only if each of the functions f1, f2, all the way up to fk are continuous. Okay. Should say is. Each of these is continuous. Part B says if f and g are continuous mappings of x into Rk, then, well, we have two results here. F bar plus G bar is continuous, and F bar dot G bar, this is the inner product, this is what this multiplication is defined, is continuous on X. Okay. So the first thing we want to prove is an if and only if statement, part A. So prove, let's let, this is for part A, let's let f1 all the way up to fk be real functions. Okay. On a metric space X, and let f bar be the mapping on X defined by So here I'll write it down as f bar of little x is equal to this k tuple, f sub 1 of x, f sub 2 of x, all the way up to f sub k of x. All right. And that's for every x in the metric space, big X. All right, so this is for part A. We're wanting to show continuity. So here, let f bar be continuous. So this is only a statement trying to prove what if f bar is continuous. Okay, we want to show that each f sub I is continuous. Okay, so here we'll let P be an element of X. We want to show that each Fi is continuous at P. So I'm going to write that down. Okay. So how do we show continuity? Well, we're going to let epsilon be greater than 0 be given. We need a definition, a delta greater than 0, such that for all x in big X with the distance in big X between x and p being less than delta, then the distance in RK of, well, this is in R, not RK. The distance in R between f sub I of x and f sub p, that's going to be less than epsilon. Okay, this metric is nothing more than the absolute value, the usual metric that we have in R. That is, we want the absolute value of, here it would be f sub I of x minus f sub I of p to be less than epsilon. I'm just spelling out what that metric in RK is. I'm sorry, in R is. Okay. Note, since f bar is continuous, and we've been given an epsilon, there exists a delta bigger than 0. Such that for all x in big X with the distance in x between x and p being less than delta, then the distance, and here it's RK, of f of x, the distance between f of x and f of p, this is bars here, will be less than epsilon. Now here in RK, we're going to use that norm. So that is for all x in x with the distance between x and p being less than delta, then here we have this norm between f bar acting on x minus f bar acting on p will be less than epsilon. Sometimes, I mean, most of the times I write down double bars here when we're in RK, but sometimes I forget, I just put a singleton, so the kind of the setting tells us what we mean by that norm here. That is, rewriting this, for all x in big X, so we're going to explicitly list out what that norm is. For all x in big X, that's where we left off, with the distance in the metric space X between X and P, and that's less than delta, we have this norm, which is the sum of the, as I runs from 1 to k, of f sub I of x minus f sub I acting on p, that's what each one of the components is, squared, that raised to the 1/2 power, that's the norm. That's going to be less than epsilon. All right. Now, we just want to show continuity for any one of these particular i's. Okay? Now, that says for a particular I. Here, let me start off. So for every x in big X with the distance between x and p being less than delta, then if you look at each one of these terms that we're adding together, because we're squaring it, that has to be greater than or equal to 0. Okay? So if you just take one of those terms, because the sum is going to be less than epsilon, one of those terms, square root, is going to be less than epsilon. So, for all x in X with the distance between x and p being less than delta, then this quantity right here is nothing more than the absolute value between this difference. This is f sub I of x minus f sub I of p. That will be less than epsilon. And this is true for each I equal to 1 all the way up to k. Thus, f sub I is continuous at p for each I. All the way up to k. And if it was continuous at p and p was arbitrary, thus I'll say f sub I is continuous on the big space, metric space, x. That's half of the part A, the proof of part A. We've got to go in the other direction now. Okay, so suppose f sub I is continuous on x. we want to show that f bar is continuous on x. So let's let P be an element of x. Okay, we want to show f bar is continuous at P. Okay, so how do we do this? Well, we'll let epsilon be greater than 0 be given. We need a delta bigger than 0, such that for all x indicates with the distance indicates between x and p, when that's less than delta, then the distance in RK, well, that's the norm between f bar of p and f bar, I shouldn't say p, I should say x here, and f bar of p, that will be less than epsilon. That's what we want. Now, since we have what we're assuming, that is that each fi is continuous, and so continuous at p. Since each fi is continuous at p, there exists a delta sub I greater than 0 such that the absolute value, such that for all x in big X with the distance between x and p is less than delta sub I, then the absolute value, this absolute value of f sub I of x minus f sub I of p, that will be less than, well, anything that I want. What I'm going to choose is epsilon over the square root of k. Remember, k is the number of components that we have. Okay, now we let let delta equal to the minimum between the collections of the d sub 1, d sub 2, up to d sub k. Then, for every x in big X with the distance in big X between x and p is less than delta, we have that f sub I of x minus f sub I of p inside absolute values will be less than epsilon over the square root of k. And this is a statement that's true for all I equal or n the set ranging from 1 up to k. So, for all x element of big X with the distance between x and p being less than this delta, here this says that the sum as I runs from 1 to k of f sub I evaluated x minus f sub I evaluated P squared raised to the 1/2 power. It was concentrated. So I haven't said anything about it yet, but I'm working on it. That's going to be equal to the sum as I runs from 1, and before I leave this, what is this? This is nothing more, before I move on, this is nothing more than the norm between F bar evaluated X and F bar evaluated P, the difference between those two. Okay. So we're saying something about it, and we hope that it's less than epsilon. Okay. Oops, I did it too far. Equals, okay, the sum as I runs from 1 to k of, here, this is the same thing as the absolute value of the f sub I acting on x minus f sub I acting on p, those guys. Each one of them to be squared and then take the 1/2 power of that. They're the same because the squaring of the difference between them, the squaring of the absolute values between them, the difference between them, is the same. Now, this is going to be less than or equal to, so really just less than. Now, each one of these guys, here's a sum, I running from 1 to k, and each one of these guys is less than epsilon over the square root of k. This will be squared, so I'm replacing this absolute value by something bigger. So the sum is going to get bigger. Take the square root of it is going to get bigger. And so that's equal to, well, in terms of the index I, this is a constant. So this would be epsilon squared over square root of k squared, which is just k. You sum that up, k times, you have k of them. And then that's raised to the 1/2 power. And of course, that's just equal to epsilon. So, summarizing, for all x in big X with the distance between x and p in big X is less than delta, then the norm between f bar acting on x minus f bar acting on p, which is what we just started working with, that will be less than epsilon. Okay? So that says f bar is continuous at p. Thus, f bar is continuous on big X. Okay, because p was just an arbitrary point. And so that ends the proof of part A. Part B. Part B, it had two parts, remember? We were talking about two vector value function. So for part B, we're going to let f bar and g bar be continuous mappings f bar of x is going to be defined to be the k tuple f1 acting on x. So we have these component functions. F sub 2 acting on x, all the way up to f sub k acting on x. And g bar acting on x is equal to, again, we have component function g sub 1 acting on x, g sub 2 acting on x, all the way up to g sub k acting on x. All right, so that's what we want. Now, we want to show, so for the first part, f bar plus g bar acting on x is continuous. Maybe I shouldn't say acting on x. Let's just say f bar plus g bar is continuous on big X. This is going to be true because of going back to the component functions when we add these two vector value functions. Okay. Namely, is that I'll say, well, f bar plus g bar acting on x, that's going to be equal to this tuple. It's going to be, well, it's going to be f sub 1, please forgive me, I skipped a step. It's f sub 1 plus g sub 1 acting on x, f sub 2 plus g sub 2 acting on x, all the way up to f sub k plus g sub k, all that acting on x. So it has k components, where each component function is the addition of the component functions from f and g, f bar and g bar. Now, since f bar is continuous, on x, then f sub I is continuous on x. Since g bar is continuous on x, then gi is continuous on x. And each one of these statements is true for all I in 1, 2, all the way up to k. Okay? And this is true by part A of this theorem. Okay. So, by a previous theorem, I think the previous theorem that I'm referring to had to do with functions to complex value functions, but it could be for real value functions as well. That we had, I think it's for real value functions, that if you have two continuous real value functions and you add them together, that's going to be continuous. We said that. For real value functions, that's what I should say. Okay, that's what we're talking about here, real value functions. Give me a second to look up that fact, just to make sure that I say it in the right setting. Yeah, we had it for complex valued functions. Okay, that's what we had it for. Okay, but that includes real value functions. Okay? And that's what we're talking about here. Okay, so by a previous theorem, f sub I plus g sub I is continuous for all I, or continuous on x, for each I in 1 up to k. And so since each one of these component functions for f bar plus g bar is continuous, then by part A, of this theorem, f bar plus g bar is continuous on x. There's one more part to this theorem. That's the second part. Okay. And that is, we want to show that f bar inner product of g bar is continuous. On x. Okay. Now let's start off. What is f bar inner product of g bar? Note, f bar inner product of g bar acting on x, that's going to be equal to a sum as I runs from 1 to k of f sub I x times g sub I of x. And that's what the inner product is. Now, since f bar is continuous on x, okay, it's continuous on x, then for each I element of 1, 2, all the way up to k, f sub I is continuous on x. Similarly, since g bar is continuous on x, then each g sub I component function is continuous on x. By a previous theorem, the multiplication f sub I times g sub I is continuous on x. So, this finite sum, as I runs from 1 to k, of f sub I acting on x, or f sub I g sub I acting on x, is continuous. Okay, what we showed was just if you add two functions together. So the functions we're adding are the f times g, f sub I times g sub I. Those types of functions we're adding together. So if you add f sub 1 g sub 1 plus f sub 2 g sub 2, that's continuous. But it's true if you add up to any finite number of continuous functions. And you show that by induction. Okay.
is continuous on x. And of course, this is nothing more than f bar dot g bar, because that's what this is defined to be, is continuous on x. All right, that ends that theorem. I next want to look at an example. So, as an example, we'll let x bar be equal to x of 1, x of 2, all the way up to x of k. And that's an element of Euclidean space, k Euclidean space. So we're going to find phi sub I acting on x bar. Okay, so really this is a, what we call phi sub I, not phi bar. It's defined to be x sub I. Then, phi sub I acting on x, defined on x bar, is continuous on its domain space is RK. And of course, it's a real value function. Okay? So let's look at the proof of this. So let's let P bar be an element of RK, where P bar is equal to P sub 1, P sub 2, all the way up to P sub K. Okay, we're trying to show continuity of this phi sub I. So to do that, we're going to let epsilon be greater than 0 be given. What we need is a delta bigger than 0, such that for all x in RK, with the distance being less than delta between it and P, so the distance here in RK is the norm, so between x bar and P bar is less than delta, then, so this is what we want, okay? Then the absolute value between x sub I minus P sub I will be less than epsilon. Okay. Now, that's the, I should have did this a little slower. So we want a phi sub I acting on x bar minus phi sub I acting on P bar, which is equal to, okay, so this is the distance in R, which is the output space for phi sub I. And phi sub I of x bar is defined to be x sub I minus phi sub I acting on P bar is just P sub I. We want that is to be less than epsilon, okay? So I just wanted to insert this word. Well, note that this x sub I minus P sub I inside absolute values is going to be less than or equal to the sum as I runs from 1 to k of the x sub I minus P sub I inside absolute values to be squared and take square root of that. And that is equal to the sum as I runs from 1 to k of x sub I minus p sub I, not an x has to be squared, raised to the 1/2 power, which is going to be equal to the norm between x bar and p bar. Now, so here, we let, we want this guy to be less than epsilon. So if this is less than epsilon, we're in good shape. So we let delta, this is what I get to control. So we let delta be equal to epsilon. So when so for any x element of Rk with x bar minus p bar inside or the norm between those is less than epsilon, then that yields that x sub I minus p sub I is absolute values, the difference between that, is going to be less than, so when this is less than delta, that means that it's less than epsilon, because they're the same, and that means this guy is less than epsilon. Okay. That's what we have. And so a conclusionary statement then is that phi sub I acting on x bar is continuous on Rk. That means that example, proof of this example. We can extend this sample and so the extension of this example, I'll just make a comment. This example and the previous theorem give the result that the function f bar acting on x bar equal to x bar is continuous on Rk. So this f bar is a function which grabs a k tuple from Rk and sends it to itself, and it's going to be continuous because its components, the phi sub i's, are continuous. Let's do one more definition and theorem, and then we'll call it quits for the day. So as a definition, a mapping F bar of a set E, okay, into Rk is said to be bounded it's bounded if there exists a real number m such that the norm of f bar acting on x will be less than or equal to m, and that's for all x in E. That's what it means to be bounded. And I'd like to look at a theorem involving boundedness. State and prove this theorem, and that'll be theorem. Suppose F is continuous it's a continuous mapping of a compact metric space X into a metric space Y. Well, I guess this doesn't have to do with boundedness yet. Then f of x, the space, big F of x, okay, the output value, that collection, is compact. That collection of output values is compact. Okay. We will later do a theorem having to do with boundedness, but it's good to have that definition now. Okay, so here's the proof. Well, we want to show that the output value, the collection of output values, f of x, that's compact. So we're going to let the collection of b sub alphas be an open cover of big F of x. To show big F of x is compact, we want to show it has a finite subcover, and so where we'll say one other thing, where F is a continuous function on x. Okay. Since F is continuous, one of the facts that we proved about continuous functions, if and only a fact, is that inverse images of open sets were open in the domain space. And so we have these B sub alphas, and each one of them is open, because the B sub alphas form an open cover. The output's space for F. Okay. Since F is continuous, then the pre-image of the B sub alpha is open in X. Okay. Now, note, X itself will be equal to the inverse image of the union of the B sub alphas. So here's the way that we think about this. The union of the B sub alphas cover the output values. Okay? And so if you look at all the little x values in big X that are sent to here, you just get all of x. But we know this is equal to the union of the inverse images of the B sub alphas. Okay. Now, that's by a homework that we did. And now here, this is open sets. These are open sets, and we're uniting them up. And they give us all of x. Okay? And so that means that the union, or these F inverse of B sub alphas, is an open cover of x. And now, since X is compact, this F inverse of the B sub alphas, okay, has a finite subcover. Or contains, I'll just say has, a finite subcover of X, say, so we have F inverse of B sub alpha sub 1, F inverse of B alpha sub 2, all the way up to F inverse B alpha sub n. Okay? So those guys are open and their union contains X. Okay? We're almost done. Okay. Okay, so f of x, big X, okay, will be contained in F of the preimage of B sub alpha sub 1 union, as a matter of fact, it's equal. Preimage alpha sub 2 union all the way up to union B sub alpha sub k. Okay? That implies that f of x is equal, it's contained in, if you will. F of, here, these unions can be rewritten as F inverse of the unions of the B sub alpha. Using a homework fact. Okay, here's alpha sub 1. We'll call it alpha sub I running from 1 to n. Okay. And that is contained in the union, as I runs from 1 to n, of B sub alpha sub I. And thus, the B sub alphas have a finite subcover of f of x. So f of big X is compact. And that means this proven. Ladies and gentlemen, that's enough for this video lecture. Thank you very much for your time and patience.